Happy Friday, everyone. I'm Brady Volpe, founder of the VolpeFirm and Chief Product Officer at OpenVault. Today, we're discussing cable TV network maintenance, mastering the 5 pillars of network maintenance, from DC to distortions. The 5 pillars covers it all. As we're going to find out from our special guest, Mr. Mike Odell, Distinguished Engineer of Comcast. Mike and I have spent a lot of time working together on Cable Lab's working groups. From what I've learned from Mike, if it's happened in the outside plant, Mike has definitely seen it. So it's great to have his insight on the show today. Mike, it's good to finally have you on. Where are you broadcasting from? And do tell us a little bit about what you do in your day job. Good to have you, Mike.
Well, thanks, Brady. It's good to finally be here. Long-time listener, first-time caller. We're coming together today from my super secret bunker in Northeast Ohio, where I work remotely for Comcast Corporate. My remote office is on my small farm in rural Northeast Ohio.
Definitely would like to see that sometime. I like the rural areas. Grew up in a rural area myself, living in the city now. So when you say your day job, and what is your day job? What do you get to play with RF still?
I do. So as you mentioned, my title is as a distinguished engineer at Comcast. I've been in the business starting as an installer almost 30 years ago now with TCI cable in the system where I still live. And over the years, then went into service and got into sweep and network maintenance. And then for the last 9 years, I've been at Comcast corporate headquarters, based in Philadelphia, but working remotely. And most recently as a distinguished engineer, just not really a difference in my area of focus, which is still the outside plant, but more of just a shift into an engineering title. So the primary responsibility is to just support our outside network maintenance technicians, which is the job that I've loved to do for a long time, in their tools, their process, their techniques, the technology itself, how we interact with it. And then, as you mentioned, we've worked a lot together in the SET and Cable Labs working groups, particularly the P&M working group. And all of the goodness that comes out of that and translating that into training and process and tooling for our technicians to help them be more efficient and effective in diagnosing and in repairing problems to take care of our customers. So I say I'm representing our network maintenance technicians in my day job.
Yeah, and I think that's something really important. You know, we talk about, oh, we're working on these Cable Labs working groups. We sit around, we talk, we joke, we have fun, but there really is an end goal to that, right? At the end of the day, we have a desire to produce documents, to uncover new ways of looking at tests that we do in our plant and how we work on things. But the end goal is to really produce things that will help our technicians understand how to troubleshoot plants better, more efficiently, maybe even come up with new ways to troubleshoot the plant for technicians. But there's a lot of complexity to that. It's not always cut and dry. It's not easy. Even in our working group meetings, we debate back amongst ourselves on like what should be the right way to talk about something, like what's the right term for some of these things, or even how do we understand, how do we think about how to troubleshoot some of these things? Because there's a lot of terms that we have, and there's a lot of tech that we have in our industry. Would you not agree?
No, you're absolutely right. And I jokingly say about some of the working groups that we're in is I try to translate. I was actually explaining this to my wife the other day. You'll enjoy this. We were driving somewhere. I actually had your podcast up on my truck on the sound system, so she was enjoying listening
Your
to
poor
some
wife.
technical. Yeah. Um, and she was asking me, "Is this what you do for every day?" I was like, "Well, kinda. My job. I feel like it's a little bit of a translator, right? Because there's some really remarkably intelligent, technical people that are engaged, like yourself and others in that working group. that are creating a lot of really great data and ways to look at data and how to visualize it and how to, pull it. And the the real art and science to this, I think, is to take that data and translate it in a meaningful way to the technicians so that they can go take an action, right,
Right.
at some point in the network. And the ultimate goal, I think, of all of us is to create the right views of the right data at the right time so that the tech can make the most informed decision about where to go and what to do, and to be as minimally invasive to the customers to, keep that connectivity on in real time. So that's the interesting part is how do you create tools and products and practices that uh, are easily consumable by the technicians, um, to make good decisions on how to take care of our customers. I think that's everybody's goal.
Right. And so you've come up, you've presented me with some cool ideas and some new ways that we can kind of approach this way to communicate things from technicians, starting with like the 5 pillars. And I think that's a unique way of doing that, because we kind of struggle with many different ways. I have so many different PowerPoints and so many different ways that I approach training technicians. And so kind of like today's show is to kind of go through what I think is a really good approach that you have to make it maybe a little bit more simple for technicians to get their arms around all the information we have in the industry, and maybe to break it down into chunks. So I think your 5 pillars is a nice way that we can kind of maybe bring technicians into the fold and allow them to kind of focus into different disciplines, yet still understand all the information that we have to take in. So I don't know if you know how we can start going into that. We'll take it a little step at a time, but I'd like to have you take us through your thoughts on that. And I think it's some really good information as we get into that.
Yeah. So I have a little bit of a confession to make here, in that, I've been in the business almost 30 years and started off in the long tree and branch architectures, and, a 300 megahertz analog one-way video system was my first experience in network maintenance. And so I learned a lot about how to interact with that type of network and how to fix different problems. And then the architecture really evolved, and so did the telemetry, right? So the ways that we measured the performance of the network changed. And it's just really continued to expand how much data is available through the DOCSIS specifications and all of this tooling. We just continued to pile on all of these data points and in this telemetry to indicate when there's a problem. And I really struggled with this for a long time. Like, what's the most important thing that we can do? Like, what's the most critical measurement or symptom that we need to go fix, right? And as the telemetry evolved, there was always this shiny new thing. When the adaptive pre-equalization data started coming back for our cable modems, we were chasing ICFRs and ripples and those kind of things. And the more DOCSIS channels that we added and, profile management applications kind of came into being, like there was all these new symptoms and all these new things and new data. And we're like, what's the most important thing we can go
I
fix?
was just going to ask you, which one was most important, Mike?
All of them is the hard part, right? And so I really started drilling down past the symptoms to the causes and tried to rationalize all of this data in a way that made sense and was simple. And what I kind of came to the realization was, Brady, is that I was doing from a process and a repair standpoint the same things in a full duplex remote PHY node plus 0 architecture that I was doing in a N plus 30 one-way architecture. The architecture didn't really matter. What mattered was like the fundamental engineering principles of coaxial cable and fiber and amplifiers and power supplies. So that's really where this whole pillar concept came came from was to say, how can we boil it down to the simplest, most basic, fundamental engineering practices? And we can't tell our technicians to go be good at 1,000 things every day. It's just not possible. Especially with the evolution of technology, like I mentioned, to the DOCSIS 4 implementations, whether it be frequency division diplexed, high split, ultra high split, or full duplex DOCSIS. The realities are the technicians of today have a really, really challenging job.
Yep.
Because all of the technology that has been deployed over the last 30 years, a lot of it's still there. We're just introducing new technology on top of previous generations of technology. So I thought about this. Our technicians could wake up in the morning and go work on RFOG, RF over glass, at one trouble call or service call, or go do an install in a mid-split system, and then have an install on a PON system, and potentially have a trouble call in an FDX system, all in the same day.
So
right?
many different technologies. And on top of it, they have to deal with customers that could be frustrated about the conditions of the plant that they're working on.
Right. And then throw Wi-Fi on top of that, right?
Yes.
So we're just talking about the backbone transport, and then the customer devices. A lot of the ways that our customers interact with it is wirelessly. So, how do we prepare our technicians to go fearlessly into the plant and say, you have the right data and telemetry to tell you what needs to be fixed, but how do we do that the most efficiently with all of the data that we have? And that's really where the whole pillars concept came from. So I've thought about this.
Well, I want to pause, and Mia, before you put up the slide, I want to pause on that for a second, because Grab a Sandwich made a comment, and Grab a Sandwich is a longtime listener, Mike. So I want to reflect on his comment, because I think it's really important. Technicians, and Mike, you made this comment about how hard it is for technicians out there. They work very, very hard, sometimes in really, really bad weather and really, really difficult conditions. And Grab a Sandwich, really, I think his comment reflects that. And he says, I'm guessing your job, Mike, must be pretty laid back at this stage in your career. Field work these days for giant corporations is awful. I envy you guys who moved up into what looks like a low-stress job. And thanks, Grab a Sandwich. I'm already going to buffer you so you don't have to say, I hope my comment doesn't sound rude. So I think it can come across as rude, but I don't believe, Grab a Sandwich, you meant it as to be rude. And we plan on doing a series later on this. It's a series that Mia is working on, where we want to talk to guys like you, Mike, who, you started off your career as a technician. You know what it's like and how hard it is to be in the field working out there. And I don't want to take up this whole session today with your career, but I think it's really important for technicians, for us first to recognize how hard the job is out there for technicians today. At the same time, there is a growth path for technicians to ultimately end up in a position like yours, but it's equally important that people who end up in a position like yours have the opportunity to do exactly what you're doing. And that is sitting back, reflecting, and understanding how hard it is for technicians out there. How can we make their lives easier now? And that, I think, is what we're talking about today.
It is. And Grab a Sandwich, thank you for your comment. Look, I can only speak for Comcast, right? I can't speak for the other operators out there, but in my position now, we get up and hustle every day. And actually our entire team was out doing field rad outs yesterday with technicians so that we stay connected to the life experience of our technicians. It is hard. We recognize that. We appreciate that. Most of us on our team at headquarters and operations came from the field. So we do fully appreciate the difficulty that job entails from being on call. I remember being on call and my wife not being happy about me getting out of bed at 2:00 in the morning to go fix an outage. And that's really what drives us, is to say, we remember how difficult that job is, to be in front of our customers every day. And to all of the expectations and requirements that the job possesses. But we also appreciate that we have a company that affords us an opportunity to get involved um, at the field level and also different aspects professionally with like Cable Labs and SCTE to help advance and grow our careers and provide opportunities to do, a job like mine. I realize how lucky I am coming from where I came from 30 years ago as an installer with TCI Cable to being, a distinguished engineer and at Comcast headquarters. Um, it's not laid back. I promise you. We're hustling every day to try and find new ways to make your job better. So it may seem like it's laid back, but we're all, working tirelessly. Not necessarily in the customer premises or in the bucket trucks anymore on a daily basis, but we do go every quarter. It's our commitment to go out and spend a day in the field with the technicians. I still climb poles. I still have my ladder and aerial lift certifications so that I can go out and do the job that I love to do, which is be a network maintenance technician, get hands on plant, fix problems, take care of customers, because we're passionate about our industry and our company. So it may seem laid back getting a chance to talk to folks like Brady about these things. But ultimately, it's our end goal is to take care of our technicians so that they can take care of our customers. So, and I do want to say, the opportunities that are out there and available to you to help develop your technical education and your expertise. That's why I'm so excited to be with Brady today on the VolpeFirm channel, because I've learned a lot from this channel. I want to continue to grow my skills and my knowledge so that I can be better for the technicians and our customers and our company. And so grab a sandwich. Thank you for taking advantage of the opportunity that's out there to hopefully learn something and to get plugged into SCT, get plugged into Cable Labs and your local chapter, because there's tons of opportunities that are available to you. And I think we'll talk more about that in the upcoming professional development series.
Thanks, Mike.
All right. So the embarrassing thing is it took me 25 years to figure out that almost every problem that I have ever fixed in the outside plant comes down to one of these 5 things. And we'll dig deeper into each of them. But the reality is, and just for clarification, we're talking about HFC networks. This is not necessarily relevant to PON, although the optical link portion of it is, and other optical networks. But in the traditional HFC network, where you have a signal origination in your head end and an optical transport out to your node, and then coaxial distribution out to your customers, whether it's N+0 or node plus whatever. The network has these 5 primary pillars that if you understand what the pillars are, what they represent, and we'll talk later about the symptoms that we can begin to connect to these 5 things. It's almost embarrassing that it took me 25 years to like go back and replay all of the weird problems that I've ever chased in the plant as the technology has evolved and the signal delivery has changed, and landed in the same 5 places that I did 20 years ago when, I first climbed into a bucket truck. So I do have them in a particular order, and we'll talk about the reasons why. From left to right, I think shielding integrity in an HFC system is the single most important thing that we can maintain. Now, impedance is next, but I really think that impedance and shielding integrity are opposite sides of the same coin. The third pillar is optical link optimization. Now, that's more relevant if you still operate analog optics. Some of the more modern optical transport, particularly Ethernet optics, link optimization is still important, but it is not quite as vital. Balancing and alignment. This is really about the amplifiers and the active portion of the plant. I have this one fourth, and we'll talk about why that is. Sweeping and balancing, when I was first getting into the network maintenance and service and sweep, was one of the single most important things that we did, especially in long cascades of amplifiers in a tree and branch architecture. Sweeping was an art, and it still is. But I think we'll discover as we go through this, if you maintain the first three pillars, the fourth one isn't quite as is important. It is important, but it's not quite as critical as we used to think. And then lastly is the power plant. Your outside plant networks, again, excluding PON, do have a requirement. They're active devices. Your amplifiers and nodes do require consistent and reliable power. So the power network is one of the pillars. So let's dive into each one of these. And I mentioned shielding integrity. I put it first. Because coaxial cable, as much as I love coaxial cable, it is inherently fragile. Our manufacturing community has done a great job of improving the quality and the performance of coaxial cables, whether they be drop cables or hardline cables. But the reality is that our systems, the modern cable television networks, are required to be closed systems. That's what allows, and Ron has referred to this a lot, the frequency reuse relationship between over-the-air broadcasters as governed by the FCC and cable television operators. We both use a lot of the same portions of the spectrum, and increasingly so. So it's important that cable television systems are closed systems. And they're closed because the coaxial cable has this thing called shielding integrity or shielding effectiveness. And it's really defined as the amount of energy or the level difference in dB between the RF energy coupled with and without the shield in place. So if you have a conductor that's shielded, it can withstand a significant amount of RF energy. And we'll look at what that level is in some very specific instances.
And that RF energy being over the air energy that could leak into the plant. Likewise, the plant could leak out if that shielding integrity is compromised. And so last Friday, we had Ron on, and he was talking about the dipole antenna and how that dipole antenna is used to pick up signals that are leaking out of the plant for egress, ingress testing. And then he also went on towards the end of the show to talk about the penalties that can happen if the FCC identifies signals that are leaking out of the plant and interfering with cellular or aircraft or anything like that. That's basically going to be interfering with other services, and that's not something that we should be doing. Is interfering with other people's signals.
No, we shouldn't. I watched that broadcast, by the way. And he mentioned, part 15, the harmful interference clause at the end. And that's very important. And I think a lot of us overlook that or don't appreciate the gravity of that. It doesn't matter whether you have a leak in the lower aeronautical or not. If your plant is an unintentional radiator and is causing interference with another licensed provider, we're obligated to fix it.
Correct.
And so, that's as a result of a shielding defect. Yes, ring crack and radial crack, good question. They're called different ththings. At the end of the day, say no to crack, kids.
Crack is bad, no matter
crack is bad.
Any form is bad.
That's right. But radial crack, ring crack, any defect to the external shield, whether it's a drop cable or a hardline cable, can result in not just egress of the system, but I tell this story a lot. I'm really interested in antennas and what's actually out in the air. And I had occasion, I was in Miami working in the field with some techs down there. And I took a really good analyzer and a dipole antenna, and I just kind of put it up in the air and surveyed how much energy is actually in the air. If you haven't done that, I will cautiously suggest that you do that, because when you do realize how much energy is actually bouncing around the air, one of two things is going to happen. It's either going to make you really diligent about the shielding integrity and the shielding effectiveness of your system, or it'll make you crawl in your basement and put on a tinfoil hat. Because there's a lot
Indeed.
out there. And especially in certain places, I bring up Miami because it's relatively flat, right? Being right on the water, there's a large population of people, and most of the stuff that's broadcast over the air is broadcast in 2 languages. So there's a lot of energy over the air. And a lot of it is in the same frequency bands that our cable television operators use. So, shielding integrity, if it's compromised, can cause a lot of problems, not just egress and harmful interference for other licensed providers, but also for the operators themselves, which translates to a poor customer experience. So when you look at the symptoms of that, and we know there's a lot of opportunity where the plant's exposed to the harmful environments, whether it's, the temperature changes and the cable expands and contracts, to squirrels, or, just the general environmental conditions that most of our outside plant exist in is pretty harsh. And so when you do have a shielding defect, it'll show up in things like ingress, which is very apparent. It can also result in ingress that you can't see underneath of your carriers.
Right.
And that's as a receive MER, right?
Or is that SNR?
So you mentioned the alphabet soup, and I do think that it's important to clarify. I don't want to get into a really nuanced discussion about the differences between SNR, CNR, MER, RXMER, but they are different. And I do think it's important that we understand a little bit of the nuance. But a lot of us that have been around for a long time just sort of think of all of it as SNR, as the generic or general industry term for signal quality. But SNR is measured very differently than CNR or MER or RXMER. But when we look at our intelligence tools, we can see that there is an impairment that's resulting in poor signal quality, whatever you want to call it, SNR, MER, RXMER.
Right.
And the likely cause is that there's some unintended carrier that's under your carrier that's resulting in that. But the cause is typically a shielding defect somewhere. It's just a matter of how you categorize and localize the symptoms of low MER, SNR, CNR, whatever you want to call it, to say where's the cause. And in most cases, you're going to find that you have a shielding integrity problem.
So back to our first pillar is the cause of the degradation that we're seeing, our MER, our SNR, or even CNR. Multiple acronyms, back to one pillar.
Right. And this one is actually CINR. In Comcast, we have this thing we call center. And the illustration in the top right of the screen shows several SEQUAM carriers with their relative receive power and also their SNR. It's actually not SNR, it's RXMER, but we illustrate it as SNR. And you can see those two channels at 597 megahertz and 603 megahertz center frequency have low SNR, even though their receive power is approximately the same as the channels adjacent to them. So it tells you that there's not a frequency-specific suck-out that's resulting in low receive power and low SNR. There's actually a carrier or energy underneath of the carrier that's degrading the SNR or the RXMER for those two channels. So that's a symptom of ingress that's resulting in poor receive MER for that device. But to your point, some of the symptoms that we'll measure could be CNR, SNR, MER, CINR. We could also see FEC, or we'll talk more about that one, I'm sure, forward error correction, whether it be correctable or failed FEC. It may show up as FM ingress because FM is still very prevalent everywhere, or high bit error rates. So those are some symptoms of shielding integrity defects. Now, I wanted to just give people some hope here, right? Because the hardline cables that we use, we've tested them in our laboratories for their shielding effectiveness in a chamber called a GTEM in our Comcast laboratory, and that top left graph there says shielding effectiveness of hardline in a cable and connector. So when properly installed and the physical and structural and electrical integrity of the cable is not affected, the shielding effectiveness of hardline cable is actually extraordinary. It can withstand, over 100, between 120 and 150 dB of over-the-air signal from intruding into the cable, which is pretty extraordinary. Now, that's when it's properly installed.
And that's a nice flat line out past the gigahertz. Do you measure out to 1.2 gig there, or just out to 1 gig, nice and flat?
This is an older screen or an older test, so we only went out to 1.2, or I think 1 gigahertz on this particular test.
Yeah.
So 1,000 megahertz.
But still, great performance.
Yeah, it's still pretty darn good. The one in the middle is actually some cables that have been stressed. So you think about your drop cable, particularly in an aerial installation that's connected from the house to the pole, and the wind and the birds and the squirrels and the snow, and all of those things cause that cable to flex over time. So we do flex our cables like 10,000 times in a machine that stresses the cables and tries to simulate the deterioration of that braided shield in Series 6 drop cables over time. And so what you see is, over time, as the drop itself flexes and moves and bends, that shield breaks down, and you'll start to see a degradation in the shielding effectiveness of that drop cable. So, we may see a piece of drop cable that looks perfectly good, our RF levels are fine, but that we have low signal quality. And it could just be because the shielding effectiveness of that flexible cable has broke down over time because of the environmentals. So when in doubt, replace the drop. The one on the right, now this is really interesting because we took that same piece of hardline cable with a properly installed hardline connector, and we started to loosen that hardline connector. And most all of the hardline connectors I see have 6 flat spots on, or 6 flat sides for the purpose of tightening. And so if you think about the circular nature of that, each one of those flat spots is about 60 degrees of rotation. So we took a perfectly tight hardline connector and loosened it 60 degrees at a time, or one flat spot at a time, and measured the shielding effectiveness of that particular connector. So you can see it went from, better than 120 dB of shielding effectiveness all the way down to about 60 dB of shielding effectiveness through one rotation. That's one 360 degree rotation of a hardline connector. So
one twist and you cut your isolation in half, basically. Yes. So, yeah, that's not so good.
No, it's not.
Tightness counts.
Keep your connectors tight. And I tell this story all the time because, we all know Ron Rannick's a genius, and I've been reading his material for years and years. He's taught me an awful lot, whether he knows it or not. And the very first time I met him was because I wanted his autograph, and I still have it. But I asked him to sign my copy of the telecommunications magazine, and he signed it, "Keep your F connectors tight, Ron Rannick." and I was expecting something really, really wise and amazing to come out of his mouth. And he wrote, "Keep your F connectors tight." Now, I'm embarrassed to say initially I was disappointed by that, but the more I thought about it, the wiser it got.
It was wise.
Oh, he's so right. So keep your F connectors tight, courtesy of Ron Rannick.
So in the context of quality of cable, Grab a Sandwich says that as someone who's worked on ancient twisted pair for 15 years before HFC, coax doesn't seem nearly as delicate as copper. Installing and repairing DSL on loops up to 5 kilometers on junk copper was so frustrating. And I think it's really interesting to see that perspective because, I always kind of looked at copper as being fairly resilient because it's been in the ground for so many years. But if you think about our coax plant, we talk about skin effect and how you shouldn't scrape the outer skin of the center conductor. But in reality, we see some really damaged plant out there, and yet the modems are still online. At the same time, he says, but a little squirrel shoe lets a lot of water in the coax. So there are scenarios where you can see a small like you said, just one rotation on a connector, and your isolation goes from a minus 120 to minus 60. So you can lose your isolation. At the same time, I know we've both seen some really mangled coax cable out there, but it's like it's the pre-equalization, the post-equalization, all of that type of error correction as we go into in DOCSIS that keeps modems and set-top boxes online. So there is built-in stuff that can kind of help with that. I don't know. What are your thoughts on copper twisted pair versus coax?
I love coax. Period. But my heart goes out to folks that have to do all the maintenance and splicing on all those twisted pairs. Oh, I've seen some pretty awful scenarios where these huge count twisted pairs get cut, in construction and car pole accidents and all that stuff. It's like, whew,
it's a lot of work.
Get comfortable. It's a lot of work. And it's similar in splice and fiber.
Fiber
right?
splice. You get a big bundle.
Yeah.
That's a lot of work.
Yeah. That's actually one of the reasons that I love coax. It's just so easy to fix. It is pretty resilient in spite of all of the conditions that it has to go through. But, it is important to recognize, what your over-the-air environment is, because it's different everywhere, right? Depending on, your population and who your local, cellular and television broadcasters and all that stuff are. So it's important to survey your local area and know what you're up against, what energy is out there. Then you'll know what frequencies are going to be affected if your shielding is affected, right? So just knowing what your over-the-air environment looks like will really help you detect. And then to your point, we have all this great software with, PMA and pre-equalization of the devices are inherently really good at managing the defect itself and mitigating that to the extent possible so that the customers don't feel it.
Until we can repair it.
Until we can repair it. But the important part is to say, when we do see a symptom that indicates that there's an impairment, like how much time do we have to actually go fix it before it continues to deteriorate? And we've been working on decay models to say what symptoms at what severity over a period of time and combinations of symptoms would give us an idea of how long do we have to go fix this before our customers start to feel it. So there's some really interesting work out there on building decay models to say this combination of symptoms in this climate and this geography, you have this much lead time before the customers start to be impacted because the software can no longer mitigate the impairment.
Right.
So I did mention impedance as sort of the other side of the same coin as shielding effectiveness or shielding integrity. And most folks don't fully appreciate the part that the cable's geometry has to play in determining the impedance of the system. And each of the individual components is critically important, and they're tuned and manufactured to be nominally 75 ohm impedance. But when you think about the cable networks as a whole, you can take and start as small as your house. Most people have multiple outlets in their house, myself included. And when you go start to add up the sum total of the individual components that go into just your drop system, think about it. You start at the tap, you have an F connector and then a segment of cable that goes to another F connector and then a ground block and another F connector, another segment of cable that goes to a splitter. If you count up the sum total of all of those parts, there's a lot, and they all need to be, impedance matched nominally about 75 ohms. And if one of them is damaged, through the environmentals or other things that we've already talked about, then the whole system is impacted. So for all the techs that are out there listening, you know as well as anybody the impact that one connector in one outlet in one house can impact potentially hundreds of people from a performance standpoint.
The entire fiber node, basically, it'll impact every
It can.
subscriber on that node. It's devastating that one subscriber can impact 100 or more subscribers.
It is. But that's also the beauty of the network, right? Is that we can service hundreds of subscribers in a service group, um, and still offer the speeds and services that they want. But you're right, the potential exists that one
Correct.
connector and one premise can affect a lot of people. Um, so impedance is really important. The geography or the shape of the cable is important. I think you did an article one time talking about the shape of the cable and the impact that you can have with a staple gun, just changing the shape of a piece of Series 6 drop cable and
Correct.
create a really frequency specific impedance mismatch. Um, so there's lots of symptoms out there where we can identify that we have impedance mismatches, and they happen organically. If you think about the thousands of interconnected components in any node or any network of any size, any hardline pin fitting that's connected to a passive device, there's multiple opportunities at every installation point to create an impedance mismatch that can then manifest itself as these pre-equalization coefficients, or as standing waves, or as suck outs, or as other things. So impedance is really, really important. I tell techs all the time, and I do it myself, just visibly and observe the network that you're working on, because if it looks wrong, it probably is. Whether it's a kink in a hardline cable on the pole, that could be from an old drip loop that wasn't formed quite right, and over time you'll see the kink that's probably, if it's not already a radial crack or a ring crack, going to become one. So just the physical geometry of the cable itself is important to maintaining 75 ohm impedance. The rest of it's the you guys did a series with Ron on the chemistry of cable and corrosion, which was a great article that he wrote years ago too. And those types of things, they can be really, really frustrating because you can't
Yeah.
physically see that corrosion, but it's causing you a problem and you can see the symptoms of it.
Yeah, and those are the problems, I think, where we turn to proactive network maintenance, because problems you can't see are the most difficult ones to solve, and I think that's where P&M can come in really. So P&M kind of helps find, we get this impedance mismatches, loose connectors, corrosion, all of these types of things. That's where P&M, we've talked about, is that a reactive tool? Is it a proactive tool? It started off being a very something that we pushed really proactively. However, it is an extraordinarily helpful reactive tool, because if you're out there trying to solve a problem and you can't see what that impairment that you just mentioned, corrosion that's hidden, P&M, it lights the dashboard up for all the modems that are being impacted by that hidden impairment. And so
Okay.
that's where we start to say, hey, here's this great proactive tool, but it works amazingly well as a reactive tool in our set of tools.
Yeah, and there are some really great tools out there, and we don't necessarily want to get into the proactive versus reactive argument today. Um,
We'll save that for another day.
Yeah, we'll save that for another day. But we do have a great suite of tools in our industry that can indicate when there's a problem. And when we consider the amount of the different symptoms that we have, visibility and availability to, we can start to build a picture along with some other software like your PMA, profile management applications, to say, when do we need to go actually, fix this? And then once we establish that priority, that's when the technicians will, obviously drive to the location and pull up their tools and say, okay, this is the problem. This is the event. These are the symptoms that are displayed. Now, how do I determine, which device I need to go interact with to repair this problem? So lots of great tools out there. I know in the interest of time, we got to keep moving. So I wanted to get into the optical link optimization pillar. Uh, Because I think this also translates over into the active device pillar too. We talked a lot in the old days of analog optics about NPR curves, that noise power ratio.
Right.
But that conversation is starting to lean into the amplifiers too, because they also have an NPR curve, and in some cases an MER curve that's very important. But one of the things that I didn't really understand as a young tech was that the analog optical link was the single limiting factor in the signal quality of any node, and that if your optical link wasn't optimized properly, then your signal quality in the node, either in the upstream or the downstream, would never be better than, whatever the NPR figure of the optics were. And so, we've spent a lot of time early on when we had these really large nodes with a lot less data, that we had to manage for noise because there were so many devices connected in a single upstream analog optical path that we wanted to avoid the laser clipping, because we didn't want to, take all of that funneled and combined noise and clip the lasers. So we tended to optimize our nodes on the lower end of the NPR curve, to avoid clipping, to give ourselves a little bit more headroom. But what we also did was limited the potential signal quality of that link.
It's a more noisy link now. You're getting into more CNR.
That's right. So It's a little bit more robust in the presence of noise, but the link itself is noisier.
Right.
And then as the service groups got smaller, we segmented node from 1x4s to 2x2s to 4x4s. The service groups got smaller. We added more upstream channels. But we left our optical links kind of in the dirt.
Yeah, and you weren't really adding any more noise, any more signal power to it, so you had plenty of headroom then.
That's right. So we've learned a lot now in more modern networks with these Ethernet optical links. That link optimization discussion changes, but the noise power discussion now kind of shifts over into the amplifiers, because as we're extending the spectrum,
we're adding a lot more signals. A lot more power to the amplifiers.
We are, and we're adding more gain to the amplifiers because we need that additional gain to overcome the attenuation at higher frequencies. So now we have these amplifiers that have a ton of gain and a lot of signal power, and we're pushing them out in higher amplitudes in both directions, that have to be properly aligned in order to avoid signal quality impairments just based on amplifier alignment, whether it be in the upstream or on the downstream. So, I mentioned sweep and balance used to be the most important thing back in the day. I hate to be that old guy that says, well, back in my day, we used to sweep and balance 30 amp cascades, but it's true. And, we had to do that a couple of times a year to make sure that these long cascades of amplifiers, their ALCs were set properly. We were still a lot of analog signal delivery. So, we wanted to make sure that the amps were set up properly to avoid, cross mod and all of those things, that your power supplies and your power supply fleet were clean and healthy to avoid hum, and those types of things where, when your ALCs aren't working properly, you get this big instability in your downstream plant. Like this image here to the right, this is downstream receive levels of a DOCSIS device over time, and you can see there's these big variations that tend to coincide with times. Overnight, when it gets cold, the signal levels go up. During the day, once it starts to heat up, the signal levels come back down, and we get into this cycle of throughout the course of the day. If your signal levels are going up and down, that's an instability that the software has a hard time keeping up with. And that's usually due to an ALC or an AGC not being set up properly.
Yeah, and that was going to be my question. Why would the ALC or AGC not be keeping those levels solid?
Well, and they could either be turned off in some cases.
Which happens very frequently. People just flip that switch to manual mode.
That's right. And forget to flip it back into AGC, or it could be malfunctioning. They do
too.
Yeah. And on the upstream, we can talk about upstream alignment But when I first started working on two-way plant, we had one carrier, and it was right smack in the middle of the band, and so it almost didn't matter what size equalizer you put in the return path. Nothing happened because the carrier was kind of right in the middle. It's like the center pivot of a teeter totter, right? The piece in the middle, as the ends go up or down, the piece in the middle doesn't change. But as we added more upstream carriers and occupied the sub split and now the mid split and soon the high split, there is more of an impact to the return path based on the equalizer than there used to be. So we have to be mindful that we're properly equalizing the entire return path, because the impacts of under equalizing it will be, less upstream path loss on the lower portion of the spectrum, which tends to be the noisiest. And it'll also mean lower transmit levels for the channels in that portion of the spectrum. So there is definitely a relationship between signal quality in your service delivery and your balancing and alignment.
As we go to like 204 megahertz in the return, do you think thermal equalization is the solution for that, or do you think it's gonna have to be active, like AGCs in the return to really hold the return solid?
I think it depends, right? If in the underground portions of the plant that aren't as subject to the dynamic changes,
No big
I
deal
think
there.
there's a place for both.
Yeah.
Yeah, but I do think that the smart amplifiers of the future are going to have AGCs in the return path too,
Yep.
because the wider and wider that gets, the more impactful that attenuation through coax becomes, and so being able to account for that's going to be even more important.
No, that makes sense.
And not to glance over the power supplies,
The
but
last pillar.
the last pillar is outside plant power. Your power supply fleet is incredibly important, and it's probably one of the more ignored portions because it has been so reliable for so long, and particularly in analog optics, that if there's intermittent fluctuations in the plant power, the optics just kind of pick right back up where they left off. But in some of the more modern networks with remote PHY, remote MAC-PHY, if there's a disruption in the power domain, these are active devices that can take 5, 10, 15, 20 minutes to reboot. So your customer downtime is a lot longer because of intermittent power disruptions than it was in previous versions of the network.
Yeah, because now with an analog fiber node, for example, power supply goes down, comes back up. That analog node is online almost instantaneously. With today's digital nodes, that power supply goes off. It's minutes before that node can come back online. And then after the node comes online, it's going to be a couple of minutes before all the modems come back online on top of that. So that turnaround time is much bigger than what it used to be.
Yeah, that's right. So we're really paying attention, to the outside plant power supplies, largely due to the customer service reliability part, but also because of the efficiency. I mean, electricity has a cost to it.
Right.
So the more efficient that you can be with your power supply selection, the more efficient that they can be, the more efficient the amplifiers are, the less your power spend will be. So it's about customer reliability in this context, but power supplies are critically important to the business. So what does it all mean? We now kind of looked at the pillars and the 5 fundamental principles of the HFC network, but all of the things that we measure from our intelligence tools and our telemetry are actually symptoms that are representative of an impairment in the network. But software has never fixed a coax problem. It can temporarily mitigate the impact of a coax problem, but it's technicians with tools that actually repair the impediments or the impairments themselves. So the causes are really important, and I say this all the time. We never actually go fix upstream FEC. And this is one of the things that I am the most passionate about is we send technicians out to nodes and say, we have a FEC problem in this node, whether it be downstream, failed FEC, correctable FEC, upstream, failed or correctable FEC. we're not actually sending them to the
How,
node to fix FEC.
how do you fix FEC, Mike?
You can't.
That's right. There's
You,
no
you
fixing
can
FEC.
you can fix a plant problem that is resulting in FEC,
Right.
right?
You got to fix
And
the root cause that's
that's
causing
right.
the FEC. The forward error correction, or code words, or pre-BER, post-BER, whatever that is that you're seeing, that's a result of
That's
something
exactly
else.
right. And so my hope is that we can really get into the craft sensitivity of the HFC network and looking at the alphabet soup of symptoms that we have. And I categorize all of the impairments that we've talked about today in one of three kind of subcategories, right? You have your data integrity impairments, your signal integrity impairments, and then your medium or your transmission medium integrity
Mm-hmm.
impairments. And I want to talk about the data integrity impairments because they are really important, and they're sort of that indication that our customers are having a poor experience. Because I've grown up through the cable business when my first system was a 300 megahertz all analog, right? It were just video signals that we were caring for. But today's networks are rapidly becoming 100% data transport networks,
Yep.
right? There are technicians at Comcast that have been here for a decade and have never worked on an analog channel.
Well, there's still analog networks, but they're transmitting data via analog signals. So just to be clear for everyone, right?
Right. Um, so when we talk about the data that's being transmitted over our network, whether it be upstream or downstream, we're really talking about data. And data integrity is critically important. And we measure it because it's so important. And we measure that in our FEC, BER. And I consider connectivity just being able to transmit, bits over the upstream or downstream, whether it's wirelessly or wireline. But that's really how we measure our data integrity impairments. Now, there's a relationship though to the channel's ability to transmit those packets error free. And in a lot of cases, the first sign of an impairment is going to be one of what I call the signal integrity impairments. That's the CNR, SNR, MERs. So when you start to see those degrade, that's an indication that, hey, there's some impairment in the network that is resulting in poor signal quality that, if left unattended, could result in a data integrity impairment. So it's a linear relationship. Now, if you want to reel that all the way back to the actual cause, based on this pillar concept, most of the causes are actually something in the physical transmission medium, which is the coaxial cable or the optical cables, or an active or passive device. And so some of the symptoms that we see that directly translate to that a damaged portion of the transmission medium itself, or that CINR that I mentioned earlier, peak to valley or frequency response, suckouts, adjacent channel power problems, waves, or leakage. And so when we start to connect the data sets that we get, the telemetry that we get, bucketize them into either data integrity problems, signal integrity problems, or transmission medium problems, then we leverage all of our test equipment, our tools, all of the things that we have at our disposal to start to tie those together. Because at the end of the day, we're looking for a portion of the network that is physically damaged, whether it be a loose corroded connector, a loose seizure screw, a loose housing, a damaged piece of cable. We have a whole suite of tools and test equipment at our disposal, MTDRs, leakage detectors, signal level meters. Don't forget the shovel,
Most
because
important.
that's right. And I've been fortunate enough to have a father and a father-in-law who were craftsmen in different things other than cable television that taught me a craftsman is only as good as his tools. And so knowing how to use your tools, whether it's your signal level meter, your MTDR, or your leakage detector, as well as your software-based tools, right, are very important to identifying what the root cause is. At the end of the day, that's what we want to do, is present you with a problem with enough information to make a really informed and educated decision, to be as efficient as possible in saying, where is the broken thing? And what broken thing do I have to fix to restore my customer service? And when you do that, the symptoms go away, right? The effect goes away. The MER gets better. And that's really what the pillars are all about, is to say, how can we correlate symptoms to causes, understand which symptoms translate to what the potential cause is, so that we can get our technicians there quicker with the right tools to solve the problem for our customers.
Okay. So if I want to put a wrap around this, then Matt, I'll get to your comment in the chat room in just a moment. So we get lots of information thrown at us as technicians, as people that are troubleshooting the plant, many different types of metrics, SNR, MER, CNR, FAC, all this information, but those are really just symptoms of the root causes, and the root causes we can break down into the 5 pillars. And so if we just take that data that we're being fed and understand this information helps us troubleshoot and get to the root causes, which can be really stacked into your 5 pillars. Mike, is that kind of a good summary of how we should take this information you provided to us?
100%. And I will say that the technology is going to continue to evolve. The symptoms, the things that we can measure, are going to continue to evolve. But as long as we have, optical fiber and nodes and coaxial cables transporting our signals to our customers, these 5 fundamental things aren't really going to change. They'll just be represented as different symptoms. So just understanding that the things that I fixed 25 years ago in my 330 megahertz one-way system are the same things that our technicians are fixing today in our 1.2 gigahertz FDX DOCSIS 4 system. The symptoms just look different.
The technology while it may be getting more complex, the underlying root cause impairments are still fundamentally the same. We just have to, if you don't know how to repair them today, just keep listening to what Mike is saying, keep watching my videos, and go to the SCTE, take their training, Cable Labs, any information that's out there for you, and you'll learn how to fix these impairments.
That's right.
So Matt, he asked the question back to when we were talking about the time it takes fiber nodes, digital fiber nodes, RPDs, things like that to boot up. I said, it's a few minutes. I mean, I have one in my lab. I know roughly how long that takes to boot up every time. He's saying he's seeing more like upwards of 45 minutes for his RPDs to boot. I kind of want to get your sense for that, because I don't want to mislead people. I think 45 minutes is a really kind of a long period of time. Mike, are you seeing nodes that's taking that long to boot up? Should technicians expect 45 minutes, or should they talk with their vendor and see why it's taking 45 minutes for their nodes to boot?
I would definitely have a conversation with the vendor if it was.
That's what I would do
minutes.
too. So I'd recommend that, Matt. Get with your vendor and see that something is out of whack there. It should not take that long.
Agreed.
Absolutely. So Mike, anything else? That was a lot of good information there.
Well, no, I did want to say thanks, Brady. First of all, for what you do with your channel. I know we share the same goal. We love the technology. We love the community that we work in, and our goal is to really help support our technicians, because there was, people over the course of my career that invested in my education, were always willing to answer my questions to help develop me both technically and professionally. And so I applaud what you're doing with your channel to help, educate the technicians. So thank you for what you do, and thanks for having me, and also for your articles in the broadband library. I know you've got another one coming up in the summer edition that I'm looking forward to.
Yep. No, you have one too, Mike, and appreciate the appreciations there. But I think we're fortunate to work in an industry where a lot of people try to contribute and help each other out and grow their career. So we do something like this. So do like and subscribe and hit the notification bell, so we can continue to help educate and promote throughout the industry. So thanks, Matt. Thanks for the thumbs up. Appreciate that. And I guess Mike, thank you for all the great information. Thanks for everyone in our chat room. And anyone, if you have additional questions for either myself or Mike, please drop those in the YouTube thing below, and we'll get back to you. And Mike, we do plan to have you back again for our career furtherment thing that we have coming up. Mia, thank you for pulling this video together and for all the videos and running this. And thanks, everyone. So take care, and we will be back next Friday with John Downey, another episode on DOCSIS. So everyone, thanks, so long, and take care.